crying. He's bad.
Yeah, we're
This is like our lit
short
class.
staffed.
Right.
How many people in your lit class?
Us three.
Yeah.
Oh, today. Normally,
There's usually six, but
Oh yeah, there's Kramer, Olivia, and
Allie.
Allie.
for now. We're
I need to buy some yellow chalk. Because the yellow is the only stuff that I can get that's in the type of chalk that doesn't like burn into the board. And this is the only piece I've left. But you can buy it's like 75 cents for a pack of 10. I just haven't got over to the store. And now that we're doing genetics and biology, and you have to like try to differentiate the mom chromosome from the dad chromosome, I started using red because it was like, well, that yellow piece is so darn tiny, it's not even going to be worth my time to do it. And the only issue is, it like burns into the board.
Yay!
So mom's chromosome made protein little t.
Chromosomes are forward.
Yeah, mom's chromosome is on the board. On the board. Her DNA is out there on full display. Did I, let's see, yesterday, I assigned problems from 33.
Yeah.
I did, okay. Any questions?
Number 20.
Number 20.
Yeah.
Yeah,
I
these ones are
still
tricky.
get these.
Here, let me just go to this general idea. So we have log base 10 of 100, and we want to know what it is. The way to answer that is to rewrite in your old form and say 10 to what power is 100? That power has to be 2. If you had log base 3 of 27, and you had to figure out what that is, what you're saying is 3 to some power is 27. What you need, what you were questioning, what you need to find out is what that power is. And in this case, of course, the power has to be 3. So if you're ever given something like this, and you have to figure out what the power is, just think 4 to what power is 16? That power's got to be 2. And then you have what that thing is. So let's take this knowledge and come over here. So f of x is 3 to the x plus 1. G of x is log base 3 of x. And we want f minus g of 3. That's way too many parentheses. A. Okay, there we go. That's better. Easier to look at. F minus g of 3. Well, that's just f of 3 minus g of 3. So I'm going to put in 3 to f and put in 3 to g. Now, if I put in 3 to f, I'm going to get 3 to the 4th power. Does that make sense?
Okay.
Right? Because that's going to be 3 to the 3 plus 1 power. And if I put in g of 3, I'm going to get log base 3 of 3. So that's 3 to the 4th. 3 to the 4th is 81, I think. That's 9 times 9. 81. And log base 3 of 3 is basically, because what you have to ask yourself the question, what does log base 3 of 3 equal? And what power would I have to raise 3 to get 3? 1. Great. Okay. 81 minus 1. So that guy's going to give us 80. Now that knowledge might be able to help us, I think, in the next phases. Because then they ask for f of g and then g of f. F of g of 3. That's f of g of 3. That's what that notation means, right? So we got to know what g of 3 is. Well, we did that last time. That's 1. So we just need to know f of 1. Put 1 into f. What do we get? 3 to the 1 plus 1 power, which is 3 squared, which is 9. The last one we gotta do is g of f of 3, which is g of f of 3. I do it all the time. I make the mini parentheses. I don't know, it makes life easier, because if you, and I can't even not do it. It's hard for me to not do it. Anyways, f of 3, we know what f of 3 is. We did that too, we got 81. So we just have, when we put in 3 to f, we get out 81, because we get out 3 to the 4th power. So now we have to do g of 81. Well, put in 81, that's going to give us log base 3 of 81. And then you got to wonder, what is that? Well, that is whatever power you'd have to raise 3 to make 81. And the power you have to raise 3 to is the 4th power. That's a good problem. If I would rate the difficulty on that problem, I would probably rate it at about an 8. And normally on a quiz or a test, you might get something around a 6. So I would think this is a good problem to really tell if you have the full grip of this. Not only of the f of g and the g of f thing, but also of the log thing. Both of those are fine. Any other questions? I'm sensing by the tearing of paper. You guys are good. We got a couple things to go over today. I'm going to skip over, I hope nobody minds, I know you won't. I'm going to skip over a few geometry ideas. It's stuff we've seen before. Example, the distance formula, right? You want to find the distance between those 2 points. Figure out the change in x. Figure out the change in y, and then you have a right triangle. Does that look familiar? You saw that in algebra, you saw that in geometry. Well, actually, you saw it in algebra, you saw it in algebra 2, you saw it in geometry. Seeing it again would just be insulting. That's my opinion. That's my opinion. Because it's not like you guys were getting C's in those classes. Right? I don't think you were. Were you? No. No. Yeah, no. Yeah. So you guys got it the first time, really. Which means when you saw it the second time, you were like, oh yeah. And then when you saw it in geometry again, you were like, okay. Like, I don't have to beat my head against the wall again, do I? No, I'm just gonna skip that stuff because it's in here, and we've actually already done it in algebra 2. How much sense does that make? I don't know, not a lot. It's in a lower numbered lesson in the Algebra 2 book than it is in the Advanced Math book. It doesn't make sense to me. John Saxon was off his rocker at times when he was putting this book together. But we don't even have to, we're not even going to cover it. We're just going to cover new stuff because new stuff is more interesting than old stuff. Right? That'd be like if you want to do a ballet class and it's like, now we're going to, well, you do pliés, but it's not like you teach pliés. Like, this is how you do a plié. No. At some point, you just start doing it. So, we're going to skip into 34. And pick up just a piece of 34. But this is the piece that we're most concerned about. And this is summation notation. One of my favorite phrases from this book. The other one is arguments and trig functions. I feel like that sounds like I feel like it sounds like a segment of a talk show. And when we come back, arguments and trig functions.
We got the courtroom. Oh, yeah.
Yeah, right? So summation notation. I feel like a computer when I do this. When I do summation notation, I feel like a computer, okay? Because you are literally following an instruction and you're doing the same instruction over and over again until you're told to stop. It's very simple. Now, to know that you're dealing with summation notation, it involves the Greek letter sigma, which is a big capital E. If I'm drawing this really carefully, it's a horizontal line, diagonal line, a diagonal line, and a horizontal line. So that's the Greek letter sigma. That's just what it is. Now, you always have a start instruction, and the start instruction will be listed below. So this is where you start. You start with I equals 1. And then you always have a stop instruction above. You will stop when you get to I equals 4. So you go I equals 1, I equals 2, I equals 3, I equals 4, stop. In this case, you have a start instruction, you have a stop instruction. And then you have a sort of a functional representation here of what it is that you're adding up. Oh, I used the word adding up. It's called summation notation, right? Sum, right? I don't want to make that seem too dumb and obvious, but when you see the sigma, this means sum. Oh, I can bring back an old story. When I was in, have I told you this one before? When I was in 7th grade, I was on this like math team, and we like competed with other schools' math teams. And that's what their jersey said on it. They were selling like t-shirts. Have some fun. Yeah, good, right? Have some fun. So that can help you remember it, that little t-shirt slogan. But anyways, start at 1, stop at 4, and you're summing up I squareds. So start at 1. If I is 1, I squared would be 1 squared. Then you go to 2. 2 squared. Then you go to 3. I squared would be 3 squared. Then you go to 4. That would be 4 squared. And then you stop. Why? Because you got to 4, and 4 was where you were told to stop. And what you do is you start at the 1, and you keep going until you reach the stop, and everywhere in between you sum up. So you're summing up lots of terms. And you add this whole thing together, and you get 1 plus 4 plus 9 plus 16, and that gives you something. 30. That's your answer. Why do I feel like a computer? Because it's just like the same thing over and over and over again, but you are told to stop at some point. So what about this guy? The sum from x equals 1 to 3 of 2x. So we're summing up 2x's, and we're summing them up starting with x equals 1 and going up to x equals 3. So start with x equals 1, you're going to get 2 times 1, which is 2. Then do x equals 2. That's going to give you 2 times 2, which is 4. Then you're going to go x equals 3. That's 2 times 3, which is 6. Then you're going to stop, because you were told to stop at 3. If you follow the directions, you'll be okay. And it's summation notation. Just for insight, there's also multiplication notation, as I'm spitting. There's multiplication notation, which is the same idea, but with a pi symbol, a big pi symbol, with stuff written below. And this would be 2 times 4 times 6, if you were curious. This is multiplication notation. Not in the book, but worth noting, should you ever see it. The only reason I bring this up, I took a geography class in college, and this came into it. Totally unexpected. And that's the only reason I bring it up, because like if you were in the class with in the geography class in college and that came up, and the guy just talks about it like it's anybody's business. I mean, I sat there as a math major and was like, what is he talking about? And somebody fortunately raised their hand. It was in a geography class after all, right? Somebody raised their hand and was like, what does that mean? Oh, it's like this. What does that mean? Oh, it's summation notation. So, but multiplication notation. Anyways, long story short, now you know. We'll go back to summation notation, do 2 more examples, and then I think we'll get it. I think we already got it for that matter. So we're doing this sum from j equals 0 to 3. That's how you read it. You would say the sum from j equals 0 to 3 of 2 to the j over j plus 1. So that's a fancy looking expression. But we do j equals 0, j equals 1, j equals 2, j equals 3, sum them all up. So j equals 0, we'll get 2 to the 0 over 0 plus 1. J equals 1. 2 to the 1 over 1 plus 1. J equals 2. 2 to the 2 over 2 plus 1. J equals 3. 2 to the 3 over 3 plus 1. Two to the 0 is 1. 0 plus 1 is 1. 2 to the 1 is 2. 1 plus 1 is 2. 2 to the 2 is 4. 2 plus 1 is 3. 2 to the 3 is 8. 3 plus 1 is 4. So it's basically 1 plus 1 plus 4/3 plus 2. Which is like 4 plus 4/3. Which is like 16/3. Kind of getting it? This last one we're not even going to simplify, but we'll write it out just to make sure that we got it. This is the sum from y equals 4 to 6 of 1 over y. Start at 4, go to 5, go to 6, stop at 6. And the expression that we're summing is 1 over y. So that should be 1 over 4 plus 1 over 5 plus 1 over 6, stop. If you so chose to put that in lowest terms and add it up, you get 37/60, of course. Right? I mean, gosh, you could throw that in the calculator, right? So I don't want to waste our time with that. And when you see this on a test, the most challenging the adding would be this. I don't want to test you on can you add numbers and fractions. I want to test you on do you know your summation notation. Say what?
I said I would make a mistake.
Yeah. Yeah, that's not, to me, that's just not exciting. The excitement is you know how to do summation notation. That's exciting. Because, I mean, just imagine for a minute, like 10 minutes ago, maybe some of you have seen this before. Has anybody seen this before?
Didn't we? Maybe not.
Physics?
Yeah, I think so.
It might have came up in physics.
Yeah, I'm pretty sure it did.
It might have came up in physics.
My goodness.
But if I just wrote that up on the board, you'd be like, what does that mean, right? 10 minutes ago? I think. You had no idea. But the cool thing about it is now you know what it means, and it's really easy, and you can just do it. So, to me, that's what I should test you on. That's what I will test you on. You actually, when you get into calculus, some of the things that you do are with sums, and one of the famous sums, it's the, well, you don't even know what a limit is, but that's okay. It's the limit as I goes from 0 to n of b minus a over n times I. Right?
It's like a fun equation.
Doesn't it? Right? This is famous. This is very famous. It's called a Riemann sum because Bernhard Riemann was the guy who formalized this process. But when you start writing sum symbols like really fast, then you start rushing, it starts looking like this. And there's actually a symbol. If you look at the board ever in study hall, you'll see a symbol that looks like this, and remove the A and the B. there's the evolution of laziness of writing sigma led to this symbol, which is now called a summa symbol for sum. Yeah, summa is the Latin word for sum. So, Gottfried Leibniz was the guy's name. He was a, Gottfried Leibniz? Gottfried, I think F-R-E-I-D. Leibniz. He was, I believe he was German, I could be wrong.
That's a great name.
Might have been French. But he was the one who, he was the one who moved us to the summa symbol. He was actually quite a well-rounded individual in addition to being a good mathematician. He was like a lawyer and.
With a name like that, you have to be.
You have to Leibniz and Leibniz. Right. That's funny. Okay, other thing that we gotta do here. This is in lesson 36. I know it's gonna feel for the rest of the year like we're jumping, because we are. Angle is greater than 360 degrees. I mean, if you think about it, when we measure angles on the XY plane, you can go around 90 degrees and get to the positive y-axis. You can go around 180 degrees and get to the negative x-axis. You can go around 270 degrees and get to the negative y-axis. You can go around 360 degrees and get all the way back to the positive or the positive x-axis. Frankly, you could just keep spinning, right? Have you ever played pin the tail on the donkey? Presumably you were spun around more than once, right? You don't get dizzy otherwise. Well, you could very easily spin around 410 degrees, right? This could be a 410 degree angle. Now at the same time, with clear mind, you can think, wait a second, if you spun me all the way around and an additional 50 degrees, you didn't have to do all that spinning. You could have just spun me 50 degrees and I'd be there. Right, because pin the tail on the donkey is, the mathematician would look at pin the tail on the donkey and say, why even spin me? I'm supposed to put the tail on the donkey. Just face me to the donkey, put the blindfold on me, and I'll pin the tail on the donkey, and the game's over. Right? Because the mathematician looks at a 410 degree angle and says, hold on a second, a 410 degree angle, take out one whole rotation, right? Think about it. If you spun 410 degrees and you took out one whole rotation, you're still facing in the same direction, right? This is the classic, the celebrities say, I went to rehab and my life took a complete 360. No, your life took a 180, right? If you took a 360, you stay in the same direction, okay, right? So this is the idea that the mathematician says, well, if your angle